Section P3, Radicals and Rational Exponents. Looking at dealing with evaluating some square roots, simplifying expressions of the form the square root of a squared, using the product rule to simplify square roots, using the quotient rule to simplify square roots, adding and subtracting square roots, rationalizing denominators, evaluate and perform operations with higher roots, and understand and use rational exponents. Some of this will be some review stuff, and some of it will be a little new stuff. So in terms of the principal square root, it says in general, if b squared is equal to a, then b is the square root of a. That's the definition of the square root principle. If a is a non-negative real number, the non-negative number b, such that b to the second is equal to a, denoted by b is equal to the square root of a, is the principal square root of a. When you're taking a square root, you are looking for the square root of a positive value. We're not getting into those imaginary numbers quite yet. So some examples. If we were to evaluate the square root of 81, we know that that is 9. If I have the opposite of the square root of 9, what times itself is 9? We'd end up with 3. So drop the negative in front, we have a negative 3. If I have a square root of 1 over 25, we can break that into a square root of 1 over a square root of 25, which would make it a little easier to see the 1 over 5. Square root of 36 plus 64, in that case you have to do what's on the inside. It's kind of like grouping symbols, we just don't put the parentheses around it. That means we would have a square root of 100, and the square root of 100 is equal to 10. And if we have a square root of 36 plus a square root of 64, the square root of 36 is going to give us 6. The square root of 64 is going to give us 8, where we get a final answer of 14. Nice, easy Algebra 1 review stuff. So simplifying the square root of a squared. For any real number a, the square root of a squared is going to equal the absolute value of a. So the principal square root of a squared is the absolute value of a. It says if a and b represent non-negative real numbers, that if you have the square root of ab, you can separate it into the square root of a times the square root of b. And if you had a square root of a times the square root of b, you can combine them together and take a square root of ab. Whichever way is easiest to simplify the problem, that's what you're looking to do. You can break them into two pieces. You can take the two pieces and put them back together and then evaluate the square root at the easiest point. So for example, if we were to simplify the square root of 75, well, this is not a perfect square. 81 is a perfect square. That would have been 9 times itself. 8 times itself is 64. So 75, it's not a perfect square. So we have to simplify it. Hopefully you know some of the perfect squares by heart, right? 1's a perfect square, 4, 9, 16, 25, 36, 49, 64, 81, 100. Those are all perfect squares. Well, when you're simplifying your square roots, again, a little review, you're looking for perfect square factors of 75 in this case. So when I look at my list, I know that 25 divides 75. So I can take this square root of 75 and I can call that a square root of 25 multiplied with a square root of 3. Well, the square root of 25 is going to give us 5. Left over is our square root of 3. If I look at the second example, we have a square root of 5x times the square root of 10x. In this case, it would make sense to multiply the numbers together and put them under 1. Well, 5 times 10 would give us 50, which we can then simplify. And I'd have an x times x, which is an x squared. Well, if I have an x squared and I'm taking the square root of that, that's just going to give us a regular x. If I take a look at the square root of 50, a perfect square factor of 50 would give us a square root of 25 times the square root of 2, which means that this is going to give us a 5. We'd have that x. Square root of 2 cannot be simplified any further. There are no more perfect square factors of that. Again, some Algebra 1, Algebra 2 review. The quotient rule for square roots says if a and b represent non-negative real numbers and b is not equal to 0, since that's on the denominator, then we could take a square root of a over b and break it into two pieces, the square root of a over the square root of b. And if we start off with a square root of a over top of the square root of b, we can put them together and simplify that way. So whichever way is easiest to get your simplified answer. So the first one, if we have a square root of 25 over 16, this would be a case that you would want to break it into your two pieces. Square root of 25 over square root of 16. Square root of 25 is going to give us 5. Square root of 16 is going to give us 4. Now my next one, I have a square root of 150x to the third over top of the square root of 2x. In this case, it might make sense to put them all under 1. So I'd have a 150 that would divide by 2. I'd have an x to the third divided by x. And then if I simplify that down a little bit, I'm looking at the square root of 150 divided by 2 gives us 75. If I have an x to the third divided by x, if you remember those exponential properties, you subtract. So if I have 3 on top and 1 on the bottom, that's going to leave us with an x squared. And I'm pretty sure we just simplified that square root of 75 into a square root of 25 times the square root of 3. And that x squared is going to just give us an x on the outside of a radical sign. So we have a 5x square root of 3. Again, this should be stuff that should be pretty simple. Algebra 1, Algebra 2 stuff. What happens if we had to do some addition and subtraction with square roots? So 2 or more square roots can be combined using the distributive property, provided that they have the same radicand. Radicand meaning the same number on the inside of that square root symbol. Such radicals are called like radicals. So for example, if I have an 8 square root of 13 plus a 9 square root of 13, when they were talking about that distributive property, they were saying if you have something that is alike, you can say 8 plus 9 is going to multiply with that square root of 13. I think it's an added step that we really don't necessarily need to show if you can visually see that you're going to add the 8 and the 9 and get a 17, and then the square root of 13 tags along. If I were to look at the subtraction, we have a square root of 17x minus 20 square root of 17x. So that first one really means I have 1 in front. I have one of those things. So I have a 1 take away 20 of these things, the square root of 17x, which means we're going to be left with a negative 19 square root of 17x. Again, review. So rationalizing denominators, that would be later on Algebra 1, definitely Algebra 2. The process of rewriting a radical expression as an equivalent expression in which the denominator no longer contains any radicals is called rationalizing the denominator. If the denominator consists of the square root of a natural number that is not a perfect square, multiply the numerator and the denominator by the smallest number that produces the square root of a perfect square in the denominator. A final answer anytime you have any problem dealing with radicals, you cannot have a square root in the denominator. So it says, continued, rational expressions that involve the sum and difference of the same two terms are called conjugates. Thus, it says the square root of a plus the square root of b and the square root of a minus the square root of b. It's the same setup, but one of them's an addition and one of them's a subtraction. Those are conjugates. If the denominator contains two terms with one or more square roots, multiply the numerator and the denominator by the conjugate of the denominator. So what does that mean? If I have a 5 divided by a square root of 3, we can't have a square root of 3 in the denominator, so we need to multiply it by something that's going to get that number out of the square root. Well, if I have a square root of 3 and I multiply by a square root of 3 on the bottom, a root 3 times a root 3 would be a root 9, and the square root of 9 is going to give us a regular integer 3. Well, I can't just multiply the denominator by a root 3. I have to multiply the numerator also by a root 3. Hopefully you understand that this fraction is equivalent to the number 1. All I'm doing is multiplying 5 over root 3 by 1, which was one of our identity properties that we talked about in a previous section. So in this case, we have the root 3 times the root 3 on the bottom. If you need to look at it this way, it really makes a root 9. 5 multiplies with that root 3, which would give us a final answer of 5 root 3 over 3. Again, you don't really need this middle step, not needed, if you can do it without. Now, when you get to looking at a sum or a difference as a denominator, that's when it got a little bit trickier. So in this case, we have 8 over 4 plus the square root of 5. And they said if you have an addition or subtraction, you're going to multiply it by its conjugate, which means we're going to multiply it by 4 minus the square root of 5. The exact same numbers, the only thing that's different is you're changing that sign. Well, whatever I do to the denominator, I'm also going to have to do to the numerator. So the top part is going to act as a distributive property. So if I have an 8 times 4, that's going to give us a 32. Take away 8 times root 5 is an 8 root 5. And then in my denominator, I'm going to go down here and do a little bit of work. So I have a 4 plus root 5 that's going to multiply with a 4 minus root 5. And if you remember back to the good old days of Algebra 1 and foiling it out, first, outer, inner, last, 4 times 4 would give us 16. The outside terms would give us a negative 4 square root of 5. The inside terms would give us a positive 4 square root of 5. And the last terms would give us a minus square root of 5 times square root of 5 is going to give us just a regular 5. So if I were to combine those middle terms, which are like radicals, that gives me 0. All I'm left with is a 16 and a take away 5, which is going to give us 11. Again, that should be some review stuff. You'll have some practice problems as you go. So the definition of the principal nth root of a real number. It has the nth root. That's a root that's other than the second root or a square root. The nth root of a is equal to b means that b to the nth power is equal to a. So it says if n, which is called the index, is even, then a is a non-negative, meaning a is greater than or equal to 0, and b is also a non-negative. If n is odd, a and b can be any real numbers. The symbol, the nth root, is called a radical, and the expression under the radical is called the radicand. So finding the nth root of perfect nth powers. Say that 3 times fast. It says if n is odd, the nth root of a is equal to a. So in this case, we have an odd power. Odd power means it could be a positive or a negative value. If n is even, then we're left with the absolute value of a. That means it's always going to be a positive answer. Just like if you take something to a second power or a fourth power or a sixth power, you always end up with a positive answer. If you had an odd power, you have the possibility of ending up negative. So it says for all real numbers, a and b, talking about the product and quotient rules for those nth roots. For all real numbers, a and b, where the indicated roots represent real numbers. Same kind of concepts that we looked at with our square roots. So our nth power, if we have the nth root of a times b, then we have the nth root of a times the nth root of b. And if we had the nth root of a times the nth root of b, we can put them together. So again, it's going to be just like what we did with our square roots. If it's easier to separate it, separate it. If it's easier to put it together, put it together. Same thing with our division. If we start with one radical, we can split them into the division of the 2 radicals, or take the 2 and put them back into 1. And again, your b is not 0. So let's try a couple. We have the third root of 40. Now this is where you have to kind of know, sorry, not the fourth root, the third root of 40. You have to know your perfect cubes. So a couple off the top of my head, I know 1 times 1 times 1 is 1, 2, 4, 8. We'd have 3 times 3 times 3, which is 27. 4 times 4 times 4 would be 64. 5 times 5 times 5 would give us 125. I'm sure we could figure out a couple more, but let's see if that will help us start simplifying. So if I were to look at that 40, what simplifies into 40? Well, 8 does. So I can take a third root of 8 and multiply it by the third root of 5, because 8 times 5 gives us our 40. Well, that third root of 8, this would have been 1 to the third, this is 2 to the third, this was 3 to the third, 4 to the third, 5 to the third. So the third root of 8 is going to give us an answer of 2, and then we're left with a third root of 5. Careful with your handwriting to make sure that doesn't look like a 23 square root of 5. Now, if I look at the next example, we're taking the third root of, we have 125 over 27. Well, if I go look at the little list that I just made, those are all perfect cubes, right? I could take this and say I'm going to find out the third root of 125 and find the third root of 27. Well, the third root of 125 is going to give us 5. And the third root of 27 is going to give us 3, and that's not so bad. One more little piece. The definition of what happens if we have fraction exponents. What if we have something like a to the m over n? So it says if the nth root of a represents a real number and m over n is a positive rational number, n is greater than or equal to 2. If n was equal to 1, you'd have no division, right? Makes sense? N had to be greater than 2 in order to have an actual fraction going on there. So what happens is they have a to the m over n is equal to, and they show two different ways that you can kind of write this out. Now, the way that Mrs. Beyerschmidt remembers this is going all the way back to when I was in high school. If I had something like a square root of 25, I remember a square root is really a power of 1/2. This is 25 to the 1/2 power. So when I look at taking a fraction and breaking it into which part is the root and which part is the exponent, I always go back to a square root. I have a 1 power on the inside and I'm taking the second root. So if we have a to the m over n, the m is going to be what the power is, and the n is going to be the root. So whatever that m is going to stay attached with that a. I'm going to mess up my notes. There we go. So then it says, furthermore, if a to the negative m over n, remember that negative exponent? If you have a negative exponent, that means you're dealing with a reciprocal, which means you have to flip some things around. So they end up throwing it as 1 over top of that a to the m over n. Let's take a look at an example to make it make sense a little bit better. If I have 27 to the 4/3, 27 to the 4/3, just like I took my square root of 25, I have a 1/2, 25 to the 1/2. That means I have 27, and what's going to be connected to the 27 is going to be the 4, and I'm going to take the third root of that. So I can write it out one of two ways. I can leave it where I have the third root of the 27 and then to the 4th power, or it might be easier to take the third root of 27 and then take that to the 4th power. You can kind of play with which one's going to be easier. Is it easier to take that 27, raise it to the 4th power, get a really crazy big number, and then have to find out the third root of that? Or could I take the third root of 27, which is going to give us 3, and take that to the 4th power? I like that second way a little bit better. 3 times 3 times 3 times 3, that should give us an 81. And the last one we're going to look at, simplifying expressions with rational exponents fractions, right? So simplify using properties of exponents. We have a 2x to the 4/3 being multiplied with a 5x to the 8/3. So I'm going to take and rearrange this problem a little bit. The commutative property tells me that I can take and multiply my regular integers together. So if I take a 2 times a 5, then I'm going to have my x to the 4/3, which is going to have multiplied with x to the 8/3. So if I take 2 times 5, that's going to give us 10. And then if I have x to the 4/3 times x to the 8/3, what happens when I have the same base? What do I do with my exponents? I'm going to add the exponents. Well, those fractions aren't too bad to add because they already have the same denominator of 3. So if I have 4/3 and 8/3, I'm going to end up with 12/3. So I have x to the 12/3. Well, 12/3 is not a simplified answer. So if we simplify that down, we end up with 10 times x to the 12 divided by 3 would give us a 4th power. Really ugly looking problem, not so bad looking answer. And let's try one more with reducing the index of a radical. So we have the 6th root of x to the 3rd. So I'm going to take and rewrite this as x, that 3rd to the 6th. Again, if you need to go back to Mrs. Beyer-Schmidt's idea of the square root, the thing on the outside tells you what the denominator is. So that means we're going to have a 3/6. So x to the 3/6, we can simplify that 3/6 to get a 1/2, which means we're going to end up with the square root of x.